We are going to be deriving the kinematic equations that you use to solve kinematics problems in mechanics for physics. These kinematic equations are ways to describe motion in situations of constant acceleration. So when there's constant acceleration, the acceleration versus time graph will be a straight horizontal line. And when there is constant acceleration, it is important to understand that since acceleration stays the point at every point in time and across any interval in time, the average acceleration will be equal to the instantaneous acceleration. So you can only guarantee that these kinematic equations are true and apply to the scenario when the scenario features constant acceleration. So this is very important. Now, acceleration, in this case average and constant since they're equal, is defined as the change in velocity over a change in time. Now, whenever you have the change in anything, it is always the final value minus the initial value. So the change in velocity would be equal to the final velocity minus the initial velocity. And these velocities are both instantaneous velocities. So it's not the average velocity. These are instantaneous final velocity and instantaneous initial velocity. Now this can also be written as what I'm going to write it as, which is v for final velocity and then v0 or v sub 0 for initial velocity. But these are essentially the same. They have the same meaning. There's different ways to write it. Now change in time should also be written as final time minus initial time. But usually when we're working with these scenarios, we can set the initial time to 0 and then reference our change in time as just the final time with the initial time set to 0. So normally we can write change in time as just t, but if our initial time is not 0, then we do have to write change in time as final time minus initial time. So with this in mind, we can rewrite acceleration here as the final velocity minus the initial velocity divided by the change in time, which is just represented as t here. And now algebraically rearranging this, we can see that at is equal to v minus v0, and v equals at plus v0 by moving it to the other side here. And this we'll call our first kinematic equation. Next, we will look at a velocity versus time graph to derive our second kinematic equation. So on a velocity versus time graph, so velocity is on the y-axis and time is on the x-axis. And since acceleration is constant, as we can see here, a change in velocity over change in time is just the same as rise over run or change in y over change in x, which is the slope of the graph. So for constant acceleration, that means the slope of this graph is constant. That means it could either be a straight horizontal line, straight positive slope, or straight negative slope. None of that matters for the derivation that we are going to do, but let's just assume that it's a straight positive slope here. Again, this slope has to be straight because acceleration, as you can see, is the slope of this graph. And since acceleration is constant, the slope is constant, which means the graph must be linear. Now, if we consider a interval of time here, like let's just say from here to here, this we have is our initial time, and then this is our final time, and this distance right here is the change in time. Now if we look, the initial time corresponds with an initial velocity here. So we'll call this v0, and this final time represents, corresponds with a final velocity, which we'll call v. Now, the height of this line right here has a height of v0, and the height of this line right here has a height of v. Now, if you notice, we define average velocity as the change in position or the displacement over a change in time. Rearranging this, we get that the displacement is equal to a average velocity multiplied by a change in time. Now, if we look at the area underneath the graph, we'll see that area is a two-dimensional quantity, and you see that one dimension here is time and the other dimension is velocity. And so the area here is gained by multiplying velocity and time, which is exactly what happens to get displacement. So we know that the area underneath this curve, even though it's a straight line, we'll call it a curve because it's on a graph, is going to be the displacement for the object in question, or the object that's represented on the graph. So we know that the area underneath here is going to be the displacement. It's a bit hard to see, but so the area is the displacement. Now, if you recognize that the area here is a trapezoid, albeit it's rotated 90 degrees, we can know that the area of a trapezoid is equal to 1/2 of base 1 plus base 2 times height. Now, if we, so if we imagine this trapezoid is being rotated, we'll see that base 1 can be v0, base 2 is v, and then the height is this change in time. So knowing that the area is equal to displacement, we can write displacement, which is equal to area, is equal to 1/2 of base 1, which in this case is v0, plus base 2, which in this case is just v, so these are the instantaneous final and initial velocities, times the height, which is the change in time, which again we'll just write as t. Now this we will call our second kinematic equation, and that is how it is derived graphically. So the displacement is equal to the area under this graph, which is basically the same as the area of a trapezoid, and that's how we get this equation. Next, knowing those two kinematic equations, let me write them down below. We have the displacement is equal to 1/2 of the sum of the initial and final velocity times the change in time, and then we have the velocity, final velocity, is equal to acceleration times time plus the initial velocity. Now, if we substitute in this equation for final velocity into this other kinematic equation here, then we get our displacement is equal to 1/2 of the initial velocity, which is here, plus the substitution we make. So plus acceleration times time plus initial velocity again, and then times time. Now, if you distribute this all out, you will find that the displacement here is equal to 1/2 of the acceleration times time squared plus the initial velocity times time. And now this is our third kinematic equation that we have derived. And so this kinematic equation eliminates the final velocity term. Next, we'll do a similar method, but instead we're going to substitute in for initial velocity. So again, we have the change in position, or the displacement, is equal to 1/2 of initial velocity plus final velocity times time. And then rearranging this equation algebraically, we find that the initial instantaneous velocity is equal to the final velocity minus acceleration times time. So substituting that in, we have the displacement is equal to 1/2 of final velocity minus acceleration times time plus final velocity, and then multiplied by time. And so we find that the displacement here is equal to final velocity times time minus 1/2 of acceleration times time squared. If you notice, that looks very similar to the equation here, except that instead of final velocity being missing, we have initial velocity being missing because we substituted in for initial velocity instead of final velocity. So this is our fourth kinematic equation. For the final kinematic equation, we'll derive it again by eliminating a term through substitution. Now, I want to iterate that these are not the only ways to derive these kinematic equations. These are just one of multiple ways. So we know that final velocity is equal to acceleration times time plus initial velocity. And we also know that displacement is equal to the sum of the initial and final velocities divided by 2 times time here. And I just moved the 2 inside, but it really doesn't matter since they're algebraically equivalent. Now, if we rearrange these equations algebraically, we find that acceleration times time is equal to the difference in the final and initial velocities. And then we find that time is equal to the difference in these velocities divided by acceleration. Next, for this one, solving for time, we get that time is equal to 2 times the displacement divided by the sum of the initial and final velocities. Now, if you notice, both equations are equal to time, so we can set these equations equal to each other. And by doing that, we get that the difference in the velocities divided by acceleration is equal to 2 times the displacement divided by the sum of the velocities. Now we can cross multiply here, and then that gives us on one side 2 times the acceleration times the displacement is equal to, and if you notice, this is a difference of squares, which means that this multiplied with that is going to be equal to final velocity squared minus initial velocity squared. Now, rearranging this, we find that final velocity squared is equal to 2 times acceleration times displacement plus initial velocity squared. And that will be our final kinematic equation. And so that is our fifth one. Next, I will list out all these kinematic equations that we have just derived. So for the first one, we know that final velocity is equal to acceleration times time plus initial velocity. For 2, we know that the displacement is equal to 1/2 of the sum of the final and initial velocities times time. And then we have displacement is equal to 1/2 at squared plus v0t. Next, we have displacement is equal to 1/2 or negative 1/2 at squared plus vt. Again, this is just rearranged. I just flipped the terms here, but it doesn't matter since they're algebraically equivalent again. And then 5, we have final velocity squared is equal to 2 times the acceleration times the displacement plus initial velocity squared. Now, the reason these 5 kinematic equations are so important is because if you notice, each kinematic equation involves 4 variables, and usually we describe the motion of objects and the position of objects using 5 variables, and those are initial velocity, final velocity, acceleration, displacement, and the time in which the action occurred, or the interval of time. Again, remember, this is just our simplification of change in time. In reality, this is final time minus initial time. So if we look at these equations, you notice that the first equation does not involve displacement. The second equation does not involve acceleration. The third equation does not involve final velocity. Fourth equation does not involve initial velocity. And fifth equation does not involve time. So when you're solving problems, they will usually give you 3 out of the 4 variables that you need and ask you to solve for a fourth. But you won't need to solve for all 5 variables for kinematics in order to answer a problem, which means that you have to look at the problem, and if the problem asks you to gives you 3 variables and asks you to solve for a fourth, you just have to recognize which variable it doesn't either give you or ask you to solve, and then use the kinematic equation that does not involve that extra variable. And that's how you choose which kinematic equation you use to solve problems. One last thing I want to uh, explain here is that displacement, again, since its change in position, is equal to final position minus initial position, which can be written this way, or similar to velocity, can be written as just x minus x0. And this x variable is just assuming that it's on an x-axis, but since these are one-dimensional equations, we can orient that axis to whichever direction we want. So usually you can just use x. But for example, if you have a falling object and you want to use change in y for displacement instead, you can do that. It doesn't matter. It's just a different variable. But this just means displacement, and these are the positions. All right, thank you very much. And these are our 5 core kinematic equations derived.